Hi everyone. The purpose of this video is to show how to carry out a thermomechanical simulation for additive manufacturing using the MOOS framework. Okay, so the purpose of this video is that we will go through the input file and we'll see an example of carrying out a like a thermomechanical simulation for a laser powder bed fusion process. So in this video I'm not covering the basics of the MOOS framework. If you want to learn more and how to install and how to run simple tutorial, you can go to the website. Okay, the focus of this video will be to show the simulation result and explain how the different blocks in the input file can create this simulation. So this is an input file, so it's a .i file, and this block corresponds to object in the simulation. And let's start with the mesh. So to create a mesh, you could use, of course, an external program like Abacus, CAE, or Gmesh. However, in this case, I show an example in which I used the generated mesh generator. So I generate a structured mesh to create a different domain that can represent the substrate and the layers. Okay. So in this case, I create a domain. These dimensions are in meters. So this is 200 by 200. Sorry, 400 by 400 micron domain, and Z will be the coordinate. So the build direction. Okay. Now let's go in ParaView to look how this domain look like. So you can see this is the domain. So you can see the structured mesh, and there are different color. Okay, that I'm gonna explain now. So you can see in terms of the mesh size. So 20 means along the x-axis there are 20 elements. Okay. And 20 elements along the y-axis, and then there are 8 elements along the z-axis. Okay, so I anticipate that the white block, so the one called block 0, represent the substrate. Okay, so how do I create such a block? So the mesh is the mesh of the entire domain. And then there are objects which are mesh modifier. Okay, you can see this object is called the subdomain bounding box generator. So it's a subdomain that is created based on coordinate. Okay, so imagine you create a bounding box where the bottom left point is given by this 3 xyz coordinate, and then the top right point is given by this 3 coordinate. Okay, so what I'm doing here is essentially picking the entire length in x and y. You see I go from minus 200 micron to 200 micron, and the same for y. And then I select only a limited height. Okay, so this one is I call it the top layer. Okay, and I assign to it a block ID, which is 1. Okay, and then there is another one. You can see this is from 120 micron to 160 micron, and it covers the entire geometry. So block 1 will be the red one. Okay, so if I delete block 1, you can see it's a domain which is on top of the substrate. Okay, and then I apply more mesh modifier. Okay, when I remove this, you can see there are these green and blue, which are two different blocks. So when I first do this operation of creating a top layer, I am actually selecting the entire domain in the z coordinate between 120 micron and 160 micron. So essentially the red will be the entire top. But then I applied two more mesh modifier, which are again subdomain bounding box generator. One is creating the first layer in the center, so it's taking as an input the top layer, you see, and is creating a set which is only in the center. I call it center because this one is from minus 100 micron to 100 micron and minus 100 micron to 100 micron, and then it goes from 120 micron to 140 micron, and then there is another one which is the same, but it goes from 140 micron to 160 micron. Okay, so in this way I take the red block that initially is it covers the entire top, and I create this block 2 and block 3. So block 2 will be the green one, you see, and block 3 will be the blue one. Okay. So this is a strategy that I've used. So essentially I created a structured mesh, and then I started dividing into domain, first by picking the top, and then by dividing the top into two smaller subdomain, which are represented the two layers. So physically, as we said, the white one is the substrate. The green one will be the first deposited layer, and the blue one the second deposited layer. While the green block, the red block, so the block 1 will be the block that is not active, so is never active, so it doesn't really represent any material. It's just there for convenience, because when I created the mesh I used this strategy with the structured mesh, but essentially block 1 will not be part of the solution. Okay, so it will remain deactivated. We'll see how to do later. So after I create this block, there are a few things that one should do. So the issue is that the default generated mesh generator in Moose will create boundaries which are external boundary of the entire domain. Okay. However, when I run the simulation, because this is a thermomechanical simulation, what I want to do is to simulate this region, so the top part of the white block as a boundary, which can, for instance, have a radiative loss. So I need to be able to apply boundary condition to this top. So I need to create a surface, because otherwise the generated mesh generator does not do that automatically. Okay, and the bounding box generator does not do it automatically either. So I use this side set around subdomain, which does what it tells. So it creates a side set around a subdomain. So as you remember, block 0 is the substrate. Okay, so you can see what I'm doing here is essentially creating a side set around the block 0 based on normal. So the 001 will be a side set which is called substrate front, and if we go to paraview and we look at it, you can see the substrate front. It's more visible if I hide the mesh. Yeah, you can see side front is essentially this surface, so it's the top surface of the substrate. So at the very beginning of the simulation, the layer will not be deposited yet, and these represent the surface of the substrate. Okay, and later we will see how during the deposition of the element one can actually obtain a modified surface. So the surface has to follow the deposited layer, okay, to model radiative and convective loss. We'll see later how to do that. So I do the same with the substrate left, substrate right, and the reason why I have to do that is because again the standard left and right surfaces created by the generated mesh generator, they are, so they cover the entire system. So they will cover also block 1, which is not really physical. So what I want to do is to create these surfaces called essentially there will be substrate left and front. We can look at it here, for instance. You can see is this so is the left surface of the substrate only, and the same is the right. Okay, the right is here, so is the is a surface that side set that I have created. Again, it's useful for boundary condition. In this case, it can be useful for mechanical boundary condition. Okay, so that's the main reason to create all these side sets, is for later being able to apply boundary condition, and I do the same with the substrate bottom and substrate top. Okay, so if you look at substrate top, will be this one, and I'm using the nomenclature of moose, so top and bottom are along perpendicular to the y axis, while the left and right are perpendicular to the x-axis, and the back and front are perpendicular to the z-axis. Okay. So yeah, given that we got this one, you see they appear also as node list. When you define a side set, sometimes in ParaView you see this node list, and they correspond to the set that one defines, but they don't have the same name that one applies in the input file. But they are there. They are usually read in by the mesh, and you can apply boundary condition on that one. Okay. So that's it for the mesh. So you see the mesh block is finished. This one is the part which is slightly more complicated than the other, but to summarize, I have created this structured mesh. Then I have divided it into 3 parts, because I want to have one part which I can deactivate, and it doesn't affect the simulation, and then I want to have the substrate, and I want to have 2 layers. Okay, because in this case I'm depositing only 2 layers. We'll see the problem block a bit later. Now we jump to the global parameters and variables. So global parameters is just really a parameter that is read by different objects. It represents the 3 displacement component which are solved by the equilibrium solver. Okay, and then there is another variable which is the temperature. So there are 4 variables in this problem. 3 are the displacement component, and 1 is the temperature, and we have equation that solve those. The temperature has an initial condition which is 293 Kelvin, while the displacement is by default initialized as 0. Okay, so the physics solid mechanics block is the block which actually defines the stress equilibrium equation. Okay, so the divergence of sigma equal to 0. This one is defining this equation. I don't go through the detail of all the options, but the most important one are the generate output. This one is an automated way to generate the output that you see in ParaView. In this case, I output the mechanical strain, and I output also the elastic strain, and I output the plastic strain components. Okay, The reason to do that is because in this case I want to have a simulation, for instance, that I can use to retrieve the inherent strain, so looking at total strain after the laser scan and elastic strain at the end, okay? And I also output the stress component, okay? So these are the output that I need to see at the end, while the variable like displacement and temperature will be output automatically, okay? So the most important option here is block. So why I set block 0? So block equal to 0 means the um, stress equilibrium equation will be solved only for block 0 and not for the other one. So as we saw, block 1 is always deactivated. So I don't really care about solving block 1. Block 1 is material that doesn't exist anyway. However, we have block 2, block 3, okay, but I'm solving the equation only on block 0. So we will see later how to do the element activation. So the element activation in Moose is made in a way that the element in block 2 and 3 will become block 0, and therefore will be solved as well when they are deposited, okay? So this is the logic. So this is why I'm solving the equation only on block 0. This flag that were at the beginning, kernel coverage and material coverage, they ensure that Moose does not throw an error, because if you don't put this flag, Moose expect that you are solving equation, you are defining the equation on every block, otherwise it doesn't know what to do if there's a block without equation. This flag ensures that this check is skipped, so you can have a mesh in which a region does not have any equation, does not have any variable, and does not have any material property, and another region has a kernel which solve a particular equation. Okay. So all that said, we jump to the kernel. So the kernel are similar to this physics solid mechanics, but this is for the heat conduction equation, and in this case I manually built the equation. So I added 3 terms to the equation. One is the time derivative, one is the heat conduction, which is essentially the Laplacian, proportional to the Laplacian of the temperature, and the third is the heat source. So the heat source will be important to define the laser source during the thermomechanical simulation, okay, and for simulating the additive manufacturing process. Essentially, these 3 blocks correspond to the heat equation that you can read, for instance, on Wikipedia. Let me find the link. So you can get essentially if you search for heat equation on Wikipedia, you will find the corresponding equation. So this is the typical equation that one would use. So you have time derivative of the temperature equal to the Laplacian of the temperature itself plus an heat source, okay. And this is represented by these 3 terms. So once again, the heat equation you can see is restricted to block equal to 0. So I want to solve for the temperature only on the substrate, and then these 2 layers will become block 0. Okay. So auxiliary variable are variables that are mainly used for visualization or for other purposes, but they are variables for which there is no specific equation. So they are auxiliary. The equation system will not include the auxiliary variable, but they are variable which have a corresponding auxiliary kernel which give them a value. For instance, the level set will be an important variable because I use it for the element activation algorithm. So I call it a level set because it will be like a variable getting value either 0 or 1, and if it's 1 in a certain at a certain coordinate, then this will be a variable that activate the element. Okay, and you can see the way I calculate level set is through a function aux. So function aux is an object which take a function as an input and give the value of the function to the variable, and the function can be a function of space and time, and I will show you later how to define it. So the volumetric heat is an auxiliary variable that will be used to visualize the volumetric heat source. Does not really it does not really affect the simulation, but is useful to for debugging, to visualize if you are defining the heat source correctly. And again, the heat source is defined only on block 0. Okay, so you can see the volumetric heat is assigned based on a material property. So this block material real aux means that there is a material property called volumetric heat, which is assigned to the auxiliary variable volumetric heat. Okay, and the material property is defined in a material object that we will see later. Okay, so these are just really for so the volumetric heat is really just for visualization. If you remove these two blocks, it doesn't really affect the simulation, while the level set is an important one because it's used for element elimination algorithm. Okay. So let's look at the boundary condition. Okay. So boundary condition can be defined in MOS using object for convective heat loss and radiative heat loss. Okay, they are already implemented in the framework, and as you can see, whenever you have a boundary condition, you need to tell which variable the boundary condition apply to. In this case, the temperature. And so the convective heat flux object is simply modeling the convection, which I can show you. So it's the Newton law of cooling. Okay, so is a law for which the heat flux is proportional to the temperature at the surface minus the temperature at infinity. So there is this T infinity means the temperature far away from the object. Okay, and then you can use a heat transfer coefficient. In this case, I use 20. The heat transfer coefficient, it depends a lot on the system you have. If you have a system where you have a ventilation, then it will increase. Okay, and you can see that I apply this boundary condition to the substrate front. So substrate front, as you remember, is the front part of the substrate. Okay, so is this bit of this part of the substrate is the top. Okay, and this, as we will see, it will be an evolving surface. So applying this boundary condition in this way ensure that even when the layer are deposited, the boundary that emit convective loss is consistent with the physics. Okay. The same thing is the radiative. So radiative is just doing something very similar to the convective, but the equation is different. Okay, so the equation for radiative heat loss is based on the Stefan-Boltzmann law. So you got an emissivity coefficient, which I set 0.24. You got a temperature infinity, and essentially it will scale as the power fourth of the temperature. Okay, so this is the Stefan-Boltzmann equation, And these are the two typical equation that you would use in a system like this. Plus I put for the temperature I put a heat sink. So I put a heat sink because this one is a very small system. So we have said before this one is only representing 400 micron of the substrate. So the substrate in reality is much bigger. So to model this, an approximation that I take is to define the Dirichlet boundary condition on the substrate left, right, top and bottom and back. Okay. So you can see I have the surface back that I didn't define because it's already defined in the generated structured mesh. So if you look at what the back is, you can see it's this one. Okay, so this is the back, but the left and right, for instance, I had to define them because they are only the substrate and not the entire block. Okay, that's why I needed to define them, but for the back you don't need to define it. So this is the heat sink approximation. Okay, I set a Dirichlet boundary condition, which means those particular surfaces are kept at 293 Celsius. Okay, they act as a heat sink. You can change this value if you want, or you can try Neumann boundary condition, but you still need to. You cannot assume that those surfaces are just free in space, because that's not real. So these are the mechanical boundary conditions. So mechanical conditions are applied on the displacement variable. Okay. And the way I decide to model this system is by defining a zero displacement boundary condition on the back. So the back is this one. So I block this surface in Z, so it cannot translate up and down. And then I block the you can see I block the substrate left and substrate right in X. So it means these two, this one and this one, cannot translate in X, which is the axis perpendicular to them. And I do the same for substrate top and bottom. So these two surfaces, this and this, cannot translate in Y, which is the axis perpendicular to them. Okay. So yeah, this is pretty much everything about the boundary condition. So I essentially block the boundaries, the external boundary of the substrate. I did not apply anything on top because it will not be appropriate, and nothing on the layer, of course. So this is a typical choice of boundary condition for simulation of laser powder bed fusion. So let's go to the material. So the material are objects that define the material property which are necessary for the equation. Okay. In this case, I have an heat conduction material. So heat conduction material is a material that feed material properties into the kernel called heat conduction. Okay. So this heat conduction kernel has some implicit input, which they are not immediately evident here, but they come from this material, heat conduction material, which requires you to define the thermal conductivity and specific heat. And these are defined by functions. So later we will see how we define this function, but essentially you need to define the thermal conductivity as a function of the temperature and the specific heat as a function of the temperature. Okay, and this one apply only on block 0, because block 0 is the only block with where the heat equation is defined. Okay, the density, so the density is some variable that is required by the heat conduction kernel again, and I keep it constant in this case because it just is a Lagrangian framework, so I assume the density remains constant during the process. Okay. So volumetric heat is creating the material property, which is called volumetric heat. So and the object that does that is the function path ellipsoid its source. So function path ellipsoid its source is a particular object which model an its source which is an ellipsoid. If you want a different shape, you can program your own object for doing that. But in this case we use the pre-existing object in Moose. So an ellipsoid, its source is just is depositing it within an ellipsoid. It has a certain characteristic radius. The decrease of the power with distance from the center of the ellipsoid is modeled as an exponential. Okay, I put 100 watt, typical for laser powder bed fusion, efficiency of 0.2. Okay, and the key point here is the path. So the path is defined by function. Okay, so there are path function that we'll see in a moment, and they define the x, y, and z coordinate of the its source as a function of time. Okay, so essentially all this information complete what is needed for the tree kernel of the heat conduction equation. So the heat conduction has a time derivative, it has the density, the specific heat, thermal conductivity, and now also the volumetric heat. Okay, so and in a moment I will show you how I define the path of the heat source. So let's go to the mechanical part. So from this part on, these are objects that define material properties which are relevant for the mechanical problem, so for the stress equilibrium. I'm not going to go in all the detail of all these options, but essentially this one is called stress, is the object that calculates the stress. Okay, as we said before, this physics solid mechanics is called an action, and is the one that solve for the stress equilibrium, so for divergence of stress equal to 0. And then you need a material object that actually define and calculate the stress, and this is this one. So it's compute multiple inelastic stress. It's called like this because one can combine this with a very complex plasticity model or inelastic model, but in this case what we do is to combine this with an inelastic model based on isotropic plasticity. Okay, so isotropic plasticity is just one of the simplest model. If you look into Moose, there are many more complex model, and you can also use other software like Black Bear as its own implementation, for instance, of Shabosh model. So there are a lot of options, but in this tutorial I'm just keeping it simple and using an isotropic plasticity. So isotropic plasticity is calculating the stress based on a yield stress function, and we'll see this one is yield stress as a function of the temperature, and an hardening function, which is the hardening rate as a function of the so it describes the hardening rate as a function of the plastic strain, and we'll see later how it is defined. And it requires a temperature, okay, because the yield stress usually decrease with temperature. You can see all these objects are again restricted to block 0, like all the material property, because the equation are only calculated on block 0, so that's all you need. And then we've got an object calculating the elasticity tensor. Okay, so Young modulus and Poisson ratio. In this case I use an object called the compute variable, so the Young modulus and Poisson ratio are not constant, but they are function of temperature. Okay, so they will be I say this particular object you can define the Young modulus and Poisson ratio as a function of any variable you like, but in this case I'm choosing the temperature. Okay, so this one you can see is something related to the eigenstrain. So the eigenstrain probably we didn't describe it before, but it's something that appears in the stress equilibrium problem. So whenever I introduce this eigenstrain name equal to eigenstrain, it means I'm passing to the problem an eigenstrain, which is in this case is the thermal expansion. Okay. So eigenstrain is in this case a material property. It will cause the thermal expansion, so the thermal stress in the simulation, and it is defined by a material object. Okay, and this material object is called the compute instantaneous thermal expansion function eigenstrain. This is a complicated way to say that you got a thermal expansion function which will depend on temperature, and you have a stress-free temperature. So at 293 you don't have any thermal strain, but then when the temperature increases you start to have this thermal expansion. Okay. So these are the material which are needed for the compute variable isotropic elasticity tensor. So it requires two material. One is called the Young modulus and the other is called the Poisson ratio, and these material are defined by this object called piecewise linear interpolation material. And you can see that I pass the variable which is the temperature, and I can define this property as a function of temperature. So for instance, you see this means x and y means x means temperature and y means the corresponding value that I want for the Young modulus. So in this case temperature 293, so room temperature, the Young modulus of my material is about 102 gigapascal, okay, and the Poisson ratio is 0.345. And then with temperature you can see the Young modulus will drop. Okay, so you need to build a lookup table, and what this material property, what this material object will do is simply interpolating linearly interpolating the Young modulus between temperature values. Okay, this is what this is doing. And then normally you don't never go to zero, right? You always keep some small Young modulus for convergence reason. The Poisson ratio it change, usually tend to increase a bit. So this is how you define this property. I've taken this from literature, so you can go. We were looking at SLM titanium alloy, possibly looking at this I need to assess this one. I think I was looking at specifically at figure 5 of this paper, but you can find the typically paper that report the actual value of the various quantity, for instance in table form, but in this case I picked the value from the graph. Okay, so from this figure you can look at high resolution and try to pick the yield stress as a function of the temperature. Okay, this is how you extract this data from the literature. And the same for the Young modulus and Poisson ratio. Okay. So the path. Let me skip the path for a moment. Let me finish the description of the material property. So this one is the K function. So the heat conduction as a function of the temperature. You can see typically in metal it will increase as a function of temperature. And then you've got the CP function. So the specific heat as a function of temperature. Again, x will be always the temperature and y the value of the property. Okay, alpha function is the thermal expansion coefficient as a function of temperature. So you can see thermal expansion is always increasing. And then I've got the yield stress. You can see yield stress as a function of temperature. So at room temperature the yield stress is 850 megapascal, and then it drops. Okay, the only one which is not a function of temperature is the hardening function. Okay, So the hardening function is essentially x is the cumulative strain, okay, and y is the increase in the yield stress. So it means when your material has reached the plastic strain of 0.1%, the yield strength has increased by about 90.9 megapascal. Okay, and this is the same. So when you reach 0.2%, your yield strength has increased by 118.1 megapascal compared with the zero plastic strain state. Okay, essentially it represents the stress strain curve plus minus an offset, which is like the zero, so minus the yield strength essentially. Time step function we come here later when we talk about the solver. Now let's go back talking about the path. So the path is really like a function. So is like a function. You can define it if you want in the same way that you define this piecewise linear. So where x will be the time and y will be the x coordinate or y coordinate or z coordinate of the heat source, but the way I do is by creating files. So let's have a look at these files. So they are these three files, and the way they look like is really just like a table format. Okay, so this one means at time 0, this is the position of the heat source. So my heat source at time 0 will be in minus 100 micron in x. Okay, so it will be in this corner. Okay, and if you go to path y, you can see where the heat source is at time 0. Okay, time 0, the y coordinate of the heat source is minus 90 micron. Okay, and it will be about here. Okay, we can go check in the solution. So this one is a simulation that I've already run. So I can, in this video I'm not covering how to run the simulation, but so let's check a moment. So if I look at the temperature initially, you can see the heat source is starting from this corner and moving along the x direction. Okay, and you can see that the motion along the x direction is expected, because I say that after 200 microsecond the heat source will move from minus 100 micron to 100 micron. Okay, so it's moving from here to here. While if I look in y, you see in the first 200 microsecond the y coordinate remain the same, and then it start changing. Okay, here I'm applying I'm using a strategy for which the heat source goes out of the geometry for some time to represent the fact that this is just a small region. So you can see at the beginning the heat source is in 100 micron, minus 100 micron, and then it jumps to 1 meter. So it means the source goes far away, okay, for some time, and then it comes back to the representative volume. Okay, but ultimately you can decide yourself where your heat source is. In my case, you see the heat source is scanning another layer of elements, and then it's moving like this. Okay, but the way you define the path is really up to you. It's just provided you understand the logic that you've got a file with you have got 3 files. The first column is time. The second column in this case is the x coordinate. The second column of y is the y coordinate, and the second column of z is the z coordinate. You see, the z coordinate I'm only doing 2 layers, so I've only got like 2 numbers which are in the middle of the two layers. Okay, You can see how this continues, so the second layer activate. We'll talk in a moment about activation, but now just assume it's activating, okay? You can see the type of temperature that you get. They will always be above the melting point, so close to the evaporation point, like about, here we got to 2300 Kelvin, okay? So this is the way the path works. So the way you can define your heat source. You can somehow automate. You can write script that can write this file for you, or you can even implement this in the C++ code if you have a particular scanning strategy that you want to implement. You will need to define a specific object instead of this one, using a specific object where the path is built into the C++ code. Okay. So that's everything for the path. Now let's look at the element activation before jumping to the talking about the time stepper and solver. So element activation, as we said, is based on this auxiliary variable called the level set. Okay, so let's go back to the simulation at the beginning. So there is a variable, an auxiliary variable called the level set. Okay. So you can see this level set, is 1 in the substrate. Okay, and this is start to be 1 also in the first layer. Okay. Probably is more visible, so it start to be 1 in the at the bottom of the first layer, you see, and then if you move forward in time, there will be the activation of the second layer. You can see that the entire region has this level set variable. Okay. So you can see now is changed. So when you activate the second layer, the level set variable in the substrate becomes 2, and the level set in the layer become 1. And the idea is that whenever this level set variable goes above 1, so it starts from 0 in the layers, but whenever it goes above 1, the element activate. So how do I do that? I define it with an expression, with a function. Okay. So there are several ways to do this type of level set, but the way I do is for instance, using if condition. So I say, okay, if the time, you see, if the time is greater than, so if time is smaller than this one, which is the initial time step, then I don't activate. Okay, I don't activate any element. And then I multiply this if for an if on the coordinate. So I say after this time I want to activate elements which are below 140 micron, and these include the first, the very first layer, but not the second. So you see at the first time step I already activated this layer. So the level set variable has become 1. Essentially it has to become 1 in the center of the layer in order to activate it. And then I put a plus, so you can do a summative approach in which you say, okay, if time is greater than this value, which is the time at which the first layer has finished depositing, then you activate everything essentially. In this way is an approximation, so I'm activating the entire layer at once. You may also want to activate the element ahead of the heat source. That's another strategy, but to do that you need to either write a more complex function or code yourself the activation as a function of some other criteria like the path. The Moose framework may have something already implemented, but activating the single layer is a simplified strategy that you can use, and it's okay because the heat source is the one that will later induce all the thermal stress. So the presence of element in the single layer will not affect strongly the residual stress prediction. So this is how I do. There are several ways you can define your level set as you like, really. But level set is a key variable in this problem because it serves to activate the element. So element activation is done by a user object called mesh modifier. Okay, this mesh modifier is called activate elements coupled. Okay, and essentially you need to pass a coupled variable to a level set and tell what is the activate value. Okay, so activate value means when this level set grows above 0.5 in the, I think in the center of the element, then the element become active. And when I mean become active, actually, so what is happening? What is happening, as you can see in ParaView, now I'm only selecting block. You see block 0, right? So if I add block 2 and 3, you can see there is essentially a I can add the block 3. So block 3 is the blue one, and then you see that block 2 has become a block 0. So if you go back at the beginning, you see there is block 0, the substrate, block 2, the green, and block 3, the blue. And then when I go to the first time step, I have the activation, so the essentially block 2 becomes block 0, and then the solver starts solving the equilibrium equation and the heat equation in the first layer. Okay, and then if you go later on, when there is the activation, you will see that block 3 becomes block 0. Yeah, this point, you see, and then it's all block 0. The other block are empty essentially, and this is captured by these two options. So the active subdomain ID, so it means the 0 is the active, so the 0 is not affected. So what this object means is that if an element which is not in block 0 and not in the inactive subdomain and not in block 1, so if an element is in block 2 and 3 and the level set field grows above 0.5 in that element, then that element is transferred to block 0, while the inactive subdomain is a subdomain that never transition. So the element in subdomain 1 never changed to 0 and never changed to anything. It's called inactive. Okay, so it's not doing anything, and that's exactly what I wanted to do when I build this geometry, right? So block 1 is just something that doesn't really represent any material in my system, so I wanted just to use it for creating the mesh in the first place, and I set it as inactive. Okay, so block 1 is inactive, while what happens is that the other one, so the 2 and 3, become 0. So this is what this object is doing. It's transferring element from one block to the other, and once the elements are in block 0, they belong part of the equation system, okay, for stress equilibrium and heat equation. So that's pretty much it. We look at the solver quickly. So there are all these post processors. So post processor is just a way to really visualize what's going on during the simulation. They're not necessary for the solver. You can delete them and you still get the final solution. But they help because you see them in the log. So in the log, I would like to see, for instance, the average temperature, the nodal max temperature, stress, mechanical stress, okay, just to understand what's going on in the simulation. And you can also use this one to find the extreme value, so maxima, minima, which can help, for instance, doing inherent strain calculation. The output block, this one is really just you can use the sync time, so output a specific time you want, or using interval. So in this case I'm outputting every 1000 time step, and you can see that's 1000 time step. If you look at the heat sources, you typically you need to choose a time step, you see. So between this situation and this situation, the solver has taken 1000 time step, which is quite a lot. It means if you want to integrate this problem properly, essentially every it takes maybe 100 of time step per element. And this is very important. Yeah, when you set the time step for the simulation, you cannot set it too big. So you need to make sure there is a good interpolation in time. So it takes many time step for the heat source to cross a single element. In this case, I think it was we went for very accurate results. So we set probably around 100, and then the solver was cutting the time step if it wasn't converging. But this is the type of requirement, which is why direct thermomechanical simulation are very computational intensive. Okay. I don't cover all the detail of the solver block, but essentially LU is a preconditioner that you would use for so it's a solver that you will use for typically for mechanical problem. You have SMP preconditioning. I don't put any line search because I think it's detrimental to the convergence actually. And then you set some. I was setting some adaptive time stepper. Okay, I don't go through all the detail, but I just want to say that this will be the typical time step that you will have in a LPBF simulation. So essentially 0.1 microsecond. Okay. Well, the total time in this simulation is only a quarter of a second, and that's because it's a very small layer. So I'm just representing a few hundred micron square of layer. Okay. And so one thing about the time step is this adaptive time step allows you to have a grow factor. So it means when the solver is converging well, it will try to increase the time step, and at the same time I don't want the time step to grow too much, so I use this time step limiting post processor. So time step limiting post processor is a post processor whose input is a function. Okay, and this function is this one. So let's go and understand what I did here. So as I said, I use this strategy for which after scanning one layer, the laser exit the geometry, in this case for about 10 milliseconds, representing the fact that is essentially this is representing a small area of a bigger component. Okay, and as you can imagine, when the laser exit the area, the simulation becomes faster. So it is a good idea to allow the solver to increase substantially the time step. So you can see this piecewise constant means from time 0 to time 200 microsecond, which is the first scan. So you can see this one, it finished at 200 microsecond. My time step need to remain 1.2 per 10 to minus 7, and this is the convergence I want. If you look at this, we already discussed this 10 to minus 7 order of magnitude, but you can relate it to the scanning speed. So for instance, you can see in this case there are 200 micron in 200 microseconds. So it means the laser is scanning at 1 meter per second. Okay, And if I choose this time step, which is about 10 to minus 7, it means in each time step its source is moving 0.12 micrometer. Okay, and my element size, as you can see, so this is 200 micron, so one of these element will be about 20 micron, so 20 micron, and each time step its source is moving a bit more than 0.1, so kind of hundreds of time step for each source to scan one element. It may be a bit too conservative, but I found that in this way I can ensure good convergence and there are no time steps that get cut. Okay, so this is more or less how you reason when you decide the time step. But then after 200 microseconds, because there is this time interval which is about 10 milliseconds for in which the laser exit the geometry, then I can increase substantially, so I can allow the time step to grow up to essentially 40 microseconds. This is the logic. So the idea is that because of how I define the heat source, you need to define a time step limiter, which is kind of it take into account of this one. If you don't do this, if you try to run this simulation just 10 to minus 7, it will be much more computational intensive. You need to use essentially the interlayer cooling. You need to use it smartly, okay, and increase the time step when you know that your system is not very hot, because when it's not very hot, you know that you can solve it more quickly and not using this time step. But in summary, this time step Fn is something that provides an upper limit to your time step. Okay, while dt is just the initial one. Okay, and then it will try to increase based on a growth factor. This one is a typical adaptive time step. The cutback factor is when it doesn't converge, it try with a time step which is half of the original time step. And that's it. Yeah, start time, end time is then time of the simulation. These are typical solver setting for the non-linear and linear iteration. Yeah, that's pretty much the file. So this is all the ingredient you need for a thermomechanical simulation. So you've got essentially all the temperature dependencies of all the quantity. These are very important to be accurate, so having proper mechanical model which is temperature dependent with the yield function, etc. Having all the thermomechanical quantity like alpha, so thermal expansion coefficient, temperature dependent, and then all the specific heat and heat conduction, which are temperature dependent as well, together with the Young modulus and Poisson ratio. So this I hope this video includes more or less all the ingredient that one need for a thermomechanical simulation, and then we can go finally to look at the result. So you can see I showed the temperature already, but one can look at more quantity. For instance, if I go looking at the stress, you can see this as solved the stress. So the stress is as expected when you start is 0, and then it starts developing. You can see when the heat source is here, there is a compressive stress along x ahead of the heat source. So you see the high temperature is here, and then the high temperature creates a compressive stress here and here, and then when it advances, you see the compressive state moves. Okay, and then when the next layer start, so the next scan start, you create compressive residual stress elsewhere. You can see the scan which create all the compressive residual stress. Okay, and this happens mostly during the scan, but then there is the cooling effect. You can see it induces this tensile residual stress here and here. Okay, so, and at the end you can assess the residual stress. Okay, when the system is cold, you need to make sure that at the end in your path, at the end there is a time. So you see, I allow the system to cool for some time. Okay, and this end time of 0.25 also include some time for cooling. In particular, if I look at the temperature at the end, you can see it has dropped substantially, and it has gone back to room temperature. Okay, and when you go back to room temperature, you can assess the residual stress. Yeah, so residual stress, you see, if you look at the x-axis, because my scan was along x, so the residual stress is so the stress induced by the heat source ahead of the heat source is compressive. But then, because it induced plastic deformation, when the system cooled down, it created this tensile, this peak of tensile stress just next to the layer. And if you look at the YY, that is, it will be tensile mostly in the perpendicular to Y. Okay, while the ZZ, as expected, will create this kind of compressive stress at the bottom. So what happens is that the system is essentially cooling, so it's bending. It's like a beam which is bending, and it creates a compression that you can see at the bottom. So in the middle, the stress along the residual stress along Z will be compressive. This is widely known from the literature. Okay, and yeah, that's pretty much it. There are other quantities they can look at. Mechanical strain and elastic strain, these are very useful if you do inherent strain calculation. You would look at the mechanical strain trading the heat source minus the elastic strain at the very end. Okay, this is how inherent strain is calculated. And then you can look at the plasticity, like plastic strain is mostly to explain what you see in the residual stress. Okay, and that's pretty much it. Yeah, this was everything I wanted to say. I hope this video can explain well the various ingredients that are required for thermomechanical analysis of additive manufacturing process in mousse. It's just one way to do that. There are many other possibilities. I want to stress that in this particular input file I have used only existing object in the mousse framework. So I did not do any coding in C++. Okay, I did not create any new object. I've only used the existing one, so this is kind of a strength of the methodology. But if you want to do something more complicated, for instance more complex heat sources or element activation, you can certainly program your own object. Okay, and that's it. Yeah, I hope you enjoyed this video, and thank you for watching.